Okay, here's the question, and try to think really carefully about this. Which of these numbers is most likely to win the lottery? So the first number is 837492216. The second number is 50491873. The third number is 123456778. And the fourth number is 77777777. Which of those is most likely to win the lottery? So you probably, good chance you already know where this is going, but here's a spoiler. The answer is they're all equally likely because they are all particular numbers, and there are 100 million possible numbers, 8 digits, 100 million possible numbers. And so, what's the chance that 1, 2, 3, 4, 5, 6, 7, 8 is going to win the lottery? It's 1 in 100 million. What's the chance that 837492216 is going to win the lottery? It's 1 in 100 million, right? Because each number is only one number, and the number of options is 100 million. So it's just a division problem, right? You divide 1 by 100 million, it's all the same either way. Okay, that's the argument. And the only interesting thing about this, you might think, is how hard it is for people to accept that this is true. Because I've gone through debates where I told someone, hey, like, this is true, they're all equally likely, right? And no matter how many times you explain the logic, it just does not compute. Like, people will not accept this reality, right? People will not accept it. It's one of those things where even if you see the steps and even if you see the logic and the chain of logic that leads this to be true, even then, it's just your brain shuts off and you're unable to accept it. So it's interesting, right? Except maybe this is not true. So let me present to you guys an argument for why actually 77777777 is more likely. Okay, here is the argument. I'm going to show some code on the screen where we compute the entropy of the different numbers, and there are different ways of computing entropy. Under Shannon entropy, all of them have the same entropy, basically, except for 77777777, because it's just counting how many times each number is repeated, basically, and so 77, that is lower entropy. But Shannon entropy doesn't really give us what we want, because Shannon entropy is basically just counting up the number of times each digit is repeated, but that doesn't capture the 1, 2, 3, 4, 5, 6, 7, 8. That is, it seems less likely than the other options. So really what we want is Kolmogorov complexity, which is saying, like, what is the length of the computer program which generates that sequence. So ideally we would use Kolmogorov complexity, but that's incomputable. We can approximate it. We could approximate using compression, but the compression approaches I see didn't really give us what we wanted. So what we could use to approximate instead is with a bespoke algorithm. What I am using here is entropy of first differences. It's the difference between each digit, and according to the entropy of first differences, then you see higher entropy for the random looking numbers, and you see lower entropy for 1, 2, 3, 4, 5, 6, 7, 8. You see low entropy for 7, 7, 7, 7, 7, 7, 7, 7. Okay, so this is capturing, yes, that the two numbers on the bottom look less random than the numbers on the top. Okay, so where do we go with that? Well, if you're playing the lottery, you're much more likely to encounter a number that is random or that looks random as opposed to a number which doesn't look random. So by virtue of the fact that one option is more likely than the other, you're more likely to get a random number, you should pick a random number. That's the argument. Okay, QED. Do you buy it? Do you accept that argument? Well, no, not at least for the original version of the problem. But there's a way of restating the problem to where it becomes more relevant. So the original problem, it was just asking you, I guess it's saying whether or not the lottery has already happened or the lottery is about to happen. So if the lottery has not happened yet, and you're picking one of these four numbers, and you have to estimate in advance when the lottery takes place, which of these numbers is most likely to show up, then the answer is yes, they're all equally likely to show up, which is the counterintuitive result, or the result which you can calculate, and it's true. The the result that people assume is true, it becomes true with a different wording of the problem. We can say, let's say the lottery has already taken place, and these are 4 numbers. One of the numbers is the actual winning lottery number. The other 3 numbers are numbers that were inserted as part of the problem. So we know one of the numbers is the real number that has already won the lottery. 3 of the numbers were inserted as part of the problem. Then, given that problem, which should you pick? Well, it's sort of flipped in that case. Yeah, you should probably pick one of the more high entropy numbers, because when the lottery takes place, there are many, many, many more high entropy numbers that can possibly win than there are low entropy numbers that could possibly win. So if you know that one of these numbers is already the winner and you don't know which one it is, then you're better off picking one of the high entropy numbers, because that is a quality that you expect to see of something that actually was the product of the lottery. And I think really it's a different question then, where the question is, how are these numbers generated? Is the number generated as a byproduct of the lottery, or is the number generated as a byproduct of the question writer inserting that number into the question? Because if it's the latter, then a human inserting the number into the question, they can pick whatever number they want. They might have a high chance of picking an ordered number, whereas the lottery most likely is going to output a disordered number. So the original question is answered by saying they're all equally likely, but I think where some people get tripped up is basically in their head they're inserting a different version of the question. And this is the most common trap with these sort of logic puzzles, is instead of reading the strict text of what it says and like not extrapolating anything else, people won't do that. They'll get the gist of the question and then they'll substitute another question in their head, which is like easier to answer, and they'll answer that question, which is equally interesting. In a way, I think computing the entropy is more interesting than just using the standard probability 1 over 100 million, right? And so we have to put in some work to figure out what is that thing that people are assuming. But they are assuming something. This is a phenomenon they talked about in Thinking Fast and Slow, where with all these tricky puzzles, the typical person who's like not trained in these puzzles, of course, they're going to substitute the question with a different version of the question that's easier to answer. Although, I think sometimes that book gets it wrong. For example, a typical problem that is presented to you in the book is, let's say, someone asks you, there are 2 possibilities. Tell me which of these possibilities is more likely. Possibility 1 is Linda is a bank teller. Possibility 2, Linda is a bank teller and is active in the feminist movement. Which of those options is more likely? And a lot of people will say that the less likely option is that Linda is a bank teller. Even though that's objectively wrong, there's a conjunction fallacy. A and B is always less likely than just A or just B. A conjunction of 2 objects is always less likely than, or less than or equal to the likelihood of one of those constituent parts just by itself. It's sort of like saying, what are there more in the world? Are there more humans, or are there more humans with 2 arms? Well, there's more humans in the world because not every single human has 2 arms, but every human with 2 arms is also a human. But I think the Thinking Fast and Slow, they actually do a pretty poor job of describing what is going on in that problem, because they have their own theory about what people are substituting, what problem people are thinking. Really what's going on there is people are reading into your question too much. When you say, which is more likely, that Linda's a bank teller or that Linda's a bank teller active in the feminist movement, people are assuming that you're implying that in the first option that Linda is not active in the feminist movement. Even though you didn't say one way or the other, people assume that you're implying that, because we do this all the time, right? We read into things. When we're communicating, communication isn't always precise. So you might ask someone like, oh, did you walk the dog, or did you walk the dog and take out the trash? Well, it's not explicit that in the first option you didn't take out the trash, but you just don't want to repeat yourself. You don't want to repeat yourself and saying, did you walk the dog and not take out the trash, or did you walk the dog and take out the trash? That sounds weird. So we omit certain descriptions, and we assume that it's implied in either case. But if you take the formal definition, then you have the conjunction fallacy and all these things. So that's one weird thing about how we understand these thought experiments, is that what people assume is actually a coherent thing. It just depends on how you word the problem. And sometimes what people assume is the problem, it could be more interesting than the actual problem you originally had.